All right, so moving on to section 9.9, we're going to talk about the convergence of Taylor series. And this might be a little bit confusing at first because you're probably thinking, well, I don't know what you're thinking, but but what you might be thinking is that, well, didn't we just talk about power series in 9.8, and we talked about we talked about convergence of power series in 9.8, right? And that's true. We talked about how to determine when a power series converges, and of course a Taylor series is just a special kind of power series. And so, we already know how to determine when a Taylor series converges. The issue is that we don't know what the Taylor series converges to. And so that's what we're going to talk about in this section, right? So recall, right, this is a Taylor polynomial, right? If you end the summation at n, then this is a Taylor polynomial, and it's an approximation for whatever function you're beginning with. And of course, the notion that we can approximate this function with a Taylor polynomial is dependent on a couple things, right? So f has to be infinitely differentiable, or at least if you're doing a Taylor polynomial, it has to be n times differentiable, right? And this approximation is only good if x is close to x naught. And how close to x naught does x need to be in order for it to be good? Well, it needs to be within, if you're talking about a series, then it needs to be within its radius, or it needs to be within its interval of convergence, right? And so we've sort of answered that question, like how close does x have to be to x naught in order for this to be a good approximation? The answer is, well, it has to be within the interval of convergence, right? But and another thing is that it might seem obvious that f of x would equal the sum as k goes to 0, as k goes from 0 to infinity of the Taylor polynomial. In other words, if you let the degree of the polynomial go to infinity, if you're looking at the series, then if this polynomial is an approximation for this function, then certainly this series is equal to the function, right? Because the approximation is supposed to get better and better and better the larger and larger n gets, right? But it turns out that that's not always true, right? So this equality doesn't always hold. In order for this equality to hold, we actually need for this series to converge, but specifically we need it to converge to f of x. We need it to converge to the function that it's trying to approximate. And that doesn't always happen. That's the crazy thing, is that doesn't always happen. So I'll give you an example here in a second. But as we saw in 9.8, not all Taylor series converge for all x. For example, the Maclaurin series for ln of 1 plus x, which we haven't actually looked at together, but you can just take my word for it that the Taylor series for this function is this series right here. And this thing, it's pretty easy to show that this thing is only going to converge if x is between -1 and +1. Okay? So that means that this series is not equal to this function if x is, say, 2 or -14 or something. Then this series is not going to converge to this function. Okay, but it will converge to the function on its interval of convergence, right? So at least it does converge, at least this series does converge to this function on its interval of convergence. But that's not even the worst possibility, because the worst possibility is this. There are some Taylor series which will converge for all x, but they don't converge to the function that they're supposed to represent. And so here's an example, right? So if you look at this kind of crazy function, f of x is e to the -1 over x squared if x is not equal to 0, and it's 0 if x equals 0. And at first glance, it might seem like, well, yeah, if you're going to define this function piecewise, then of course crazy things are going to happen. But actually, this piecewise definition is not that crazy because e to the -1 over x squared is undefined when x is 0, right? Because then you'd have a 1 over 0, and so that quantity is undefined. And so you need, in order to get this function to be defined for any real value x, you need a different rule for the function when x equals 0. And the rule that you should assign when x equals 0 is 0, because if you look at this thing in Desmos, right, this is the function e to the negative 1 over x squared, and obviously the limit as x approaches 0 is 0. So it seems like that's the natural, that's sort of like the natural definition to give to the function. That's the natural kind of function value to assign to the function when x equals 0. So we've got this function, and it's really not that crazy of a function once you think about it. And furthermore, if you define the function this way, then you get a function that's continuous everywhere, right? Differentiable everywhere. It's even differentiable at 0, right? Now, I'm not going to go through all the nitty-gritty details of calculating the derivative of this thing at 0, because that's a little complicated because it's all piecewise and everything. You have to use the limit definition in order to really get it. And you're welcome to kind of work this out on your own. If you do work out the derivatives, you find that the derivative at 0, all of the derivatives of this function at 0, so the first derivative, the second derivative, the third derivative, the kth derivative, they're all just 0. So f prime of 0 is 0, f double prime of 0 is 0, f triple prime of 0 is 0, right, and so forth. So what does that mean? That means the Maclaurin series for this function is going to be the sum from k equals 0 to infinity of the kth derivative of f at 0 divided by k factorial times x to the k. But the kth derivative of x at 0 is 0 for all k, right? Which means this is just going to be 0 plus 0 plus 0 plus 0, right? It's just going to be 0. So the Maclaurin series for this function is 0, which obviously it converges. It converges for any value of x, right? It converges, but it converges to 0. It doesn't converge to f of x, okay? Anyway, all of this to say that we can't just take it for granted that this equality is going to hold. Even if the series converges, it's not necessarily the case that it converges to f of x. Okay? So we can't just take this for granted. And so the question becomes, well, how do we figure out what the series converges to? We can figure out, using the methods from 9.8, we can figure out that the series converges, or diverges, right? We can figure out where it converges. But how do we figure out what it converges to, right? Because in order to say that f of x equals this thing, you have to establish that this converges and that it converges to f of x. So how do you figure out that it converges to f of x? Well, the following theorem is going to tell us how to know if a function's Taylor series converges to the function that it's meant to represent. And so this is theorem 9.9.2 from your textbook. And it turns out that this series is going to converge to f of x, right? So this equality holds at a point x if and only if the limit as n approaches infinity of the remainder is equal to 0. So if the remainder goes to 0, then we can conclude that this series equals the function that it's supposed to represent. So again, just to remind you, r sub n of x represents the nth remainder. The nth remainder is the original function minus the nth Taylor polynomial meant to represent the function. And again, the nth Taylor polynomial is this thing. So it's f of x minus the nth Taylor polynomial, right? So if this remainder, if the limit as n approaches infinity of this remainder is 0, then you can say that the Taylor series equals the function that it was built to represent. Okay? Now, in order to use this theorem, it's helpful to recall a previous theorem from section 7, so from theorem 9.7.4, which we looked at and which said this, right? So the absolute value of the nth remainder is going to be less than or equal to m over n plus 1 factorial times x minus x naught to the n plus 1, where m is an upper bound on the n plus first derivative evaluated at x. Okay, so that's a useful that's a useful theorem to keep in mind when you're trying to apply theorem 9.9.2, and I'll show you why with an example. So let's take a look at example 1. It says, show that the Maclaurin series for cosine x converges to cosine x, right? So not just that it converges, but specifically that it converges to cosine x, right, for all x. So in other words, show that cosine x equals this thing for all x between negative infinity and positive infinity. So let's do it, right? So this is example 1. And our claim is that cosine x equals the sum from k equals 0 to infinity of -1 to the k times x to the 2k over 2k factorial. Right? So that's the claim that we want to try to show. Well, we've already shown that this thing converges for all x. So I'm not going to do that again. Actually, I don't know if we've shown that together, but it's easy to do, right? So maybe I'll say this. First of all, converges for all x because, well, if we apply the ratio test, right, we would get limit as k approaches infinity of x to the 2 times k plus 1 over 2 times k plus 1 factorial times 2k factorial over x to the 2k. And that's limit as k approaches infinity of x to the 2k plus 2 over 2k plus 2 factorial times 2k factorial over x to the 2k. And I'm going to be a little bit sloppy here and just say, okay, so here I would have 2k plus 2 times 2k plus 1 times 2k factorial. And so that factorial is going to cancel with that 2k up there. Here I would have x to the 2k times x squared, and the x to the 2k's would cancel. So I think at the end of the day, what I'm going to end up with is, so that's gone. I'm going to end up with an x squared here. Oh, and I should have absolute values around all of my x's, right? But anyway, the absolute value of x squared is still just x squared. So I can drop the absolute values at that point. Anyway, but I'm going to have an x squared, and then down here I'm going to have 2k plus 2 times 2k plus 1. And that equals x squared times the limit as k approaches infinity of 1 over 2k plus 2 times 2k plus 1. This thing goes to 0, so this just equals 0. And that's less than 1 for all x. Right? So by the ratio test, right? So first of all, this thing converges for all x by the ratio test. Maybe I can say by the ratio test. Right? By the ratio test. Okay. So it converges, but that's only half the battle, right? Because it needs to converge to cosine x, right? How do we show that? Well, we show that by applying this theorem right here. We have to show that the limit of the remainder is 0, right? Now, in order to show that the limit of the remainder is 0, I'm going to use this theorem here. So first I need to try to bound the n plus first derivative, right? So, okay, so now note that the kth derivative of x, well, maybe, I never did call this thing f of x, did I? So maybe I should do that. So note note that if f of x equals cosine x, then the kth derivative of x is either going to be, well, first derivative is negative sine, second derivative is negative cosine, third derivative is positive sine, fourth derivative is positive cosine, and then they're going to alternate back and forth, right? So the kth derivative of x is either plus or minus cosine x, or it's plus or minus sine x, right? What I need to do is bound the absolute value of that thing. So I can say, so absolute value of the n plus first derivative is either cosine or it's equal to sine. Okay? In either case, absolute value of the n plus first derivative is going to be less than 1, right? Because sine and cosine are both between -1 and +1 all the time, right? So their absolute values are going to be, between 0 and 1, right? So this thing is less than 1. And so 1, that's our upper bound, n. Okay? So the remainder, the absolute value of the remainder, is less than or equal to m, which is 1. Okay? I'm using this fact right here, right? Theorem 9.7.4. So it's m over n plus 1 factorial times x minus x naught. Well, x naught in this case is 0 because we're dealing with the Maclaurin series, right? So this is just absolute value of x to the n plus 1. Okay, I'm sorry. I need to let my dog out. Okay. All right. So we were here. Okay. So absolute value of the remainder is less than or equal to this expression. Well, note that this expression is just absolute value of x to the n plus 1 over n plus 1 factorial. Now, one of the things that you proved in the homework is that limit, what homework assignment was it? Goodness, I feel like it was way back in like section 9.2. But one of the things that you should have proven as, it was like exercise 31 from 9.2 or something like that. And one of the things that you should have proven is that limit as n goes to infinity of absolute value of x to the n over n factorial equals 0. And if that's true, then this limit is also equal to 0, right? Now, how does that help us, right? Well, it helps us because of the squeeze theorem, right? So we can say 0 is less than or equal to absolute value of the remainder, which is less than or equal to absolute value of x to the n plus 1 over n plus 1 factorial. And so now if you take the limit as n goes to 0, or sorry, as n goes to infinity of 0, then you know that limit as n goes to infinity of 0 is just going to be 0. And this limit is 0 because of the work that you did way back in like section 9.2. Okay? So by the squeeze theorem, this limit is equal to 0. Okay, so we know that the series converges, and we know that it's the limit as n goes to infinity of the nth remainder is 0. So the remainder, right, which is the difference between the function and the Taylor polynomial that's meant to approximate it, that remainder is disappearing, right? Which means that the polynomials, as n gets larger and larger and larger, the polynomial is getting closer and closer and closer to the actual function value itself, right? So the series converges and the remainder is disappearing. So that means the series must be converging to the function that it's supposed to represent, right? So thus, sum from k equals 0 to infinity of -1 to the k times x to the 2k over 2k factorial converges to cosine x by theorem 9.9.2. Okay, and that's the end of the proof, right? So there you go. That seems like a lot of work and a lot of stuff, but really, this wasn't really necessary because I'm almost certain that we've seen this before. I just wanted to be absolutely sure that we'd seen all of that. This is the new stuff, and it's really not that much. Basically, we're just trying to show this result right here. Okay. And the way that you do that again is that you have to find some upper bound for absolute value of the n plus first derivative of f evaluated at x, right? Which in this case, that upper bound was just 1. Then if you can do that, it's usually not too bad to show that this thing goes to 0. Okay. Assuming that you're working with a function that actually does converge, or a Taylor series that does converge to the function it's meant to represent. But anyway, that's that. Now I wanted to show you this in Desmos because I think it's not that one. I wanted to show you this in Desmos. So the green is cosine x, and the red is the Taylor polynomial that is supposed to represent cosine x. And so here I'm ending at 0, from 0 to 0. So this is like, obviously, you just get 1, right? So that's not a very good approximation. But if I let p go to 1, then I get this quadratic, which you can see within a certain interval is not a bad approximation. If I zoom in, I mean, it's pretty good, right? Like, there's not a lot of error there at all. If I let p go to 2, then you get that cubic, okay, which is even closer. In fact, I'm going to zoom in on this spot right here so that you can see. Right? So there is a little bit of a difference between the Taylor series in red and the function it's supposed to represent in green. But this is only if p equals 2, right? If I let p be 3, then, like, you see how quickly it converged? We're only at p equals 5, and it's already indistinguishable. If I zoom in more, man, you still can't even see the difference. Oh, there it goes, there it goes. Okay, so I have to zoom in really far. I'm going to zoom in as far as Desmos will let me and see how fast it takes to close the gap, or how long it takes to close the gap. So just 2 more. Oh, goodness. I'm not sure. Oh, that's as far as Desmos goes. So at p equals 8, this is already beyond Desmos' ability to even distinguish the difference, at least when you're this close to 0. And let me zoom back out. Okay, and look what's happened to the polynomial, right? So to this red thing. Just watch this thing get bigger and bigger. It's really cool. It just like works outwards and kind of swallows up the cosine ooh, it's Desmos is having a hard time like doing the calculations, starting to glitch out a little bit, but that's just so cool. I think that's really awesome. So yeah, so this series definitely converges to cosine x. If you let p go to infinity, then this thing equals this thing, right? Which is just insane. One of the coolest results. I'm going to start again so you can see that work out. It's just so cool. I love it. Okay, well anyway, whoops. All right, so back to business though. Okay, so we've done this. So we've shown now that this Maclaurin series equals the function cosine x. In a similar way, we can show that equality holds for each of the series in table 9.9.1, which is on page 589 of your textbook. So let me pull that up. All right, so that's right here. So this is just a table that lists a whole bunch of really kind of commonly used Maclaurin series. A lot of these things we've kind of gone over and proven together. Some of these things we haven't. Like I don't think we ever looked at sinh and cosh together. We didn't look at this binomial one down at the bottom, but I'm going to talk about it here in a second. But definitely we've talked about e to the x, sine x, cosine x, right? Anyway, so you should memorize these, right? You should make little index cards and commit them to memory, right? So you should know that 1 over 1 minus x equals, you know, the sum from k equals 0 to infinity of x to the k. And that, well, maybe not this one so much because I don't have this one memorized myself. But e to the x I have memorized, sine x, cosine x, right? These are pretty standard ones. So, and you can prove that these equalities hold in the same way that we just did example 1, right? So you can prove that the equality holds. Over here they also list the interval of convergence, which is nice. So this equality holds, you know, provided that x is between -1 and +1. This equality holds for any real number x, right? And so forth. These series are really useful. Well, actually, let me modify that. The polynomials, the Maclaurin and Taylor polynomials are really useful. They're really useful to approximate the values of different things. Okay, and let me give you an example of that. So, for example, how do you calculate sine of 3 degrees? Like when you punch sine of 3 degrees into your calculator, what is it doing, right? Like how does it figure out that value? Well, first of all, it'll take 3 degrees and change it into radians, okay? So you have sine of pi over 60, and then it'll apply this Maclaurin series for sine, right? So since sine equals this Maclaurin series, sine of 3 degrees would just be, well, notice if you plug in 0, you just get x, right? So if x is pi over 60, then you get pi over 60. When you plug in 1, you get negative x cubed over 3 factorial. But x is pi over 60, right? So you plug in pi over 60 cubed over 3 factorial. Then if you plug in 2, you get pi over 60 to the 5th over 5 factorial. Then minus pi over 60 to the 7th over 7 factorial, and so forth. So your calculator will do this out to a certain number of terms, right, in order to get the desired level of, accuracy. By the way, to achieve any desired level of accuracy, we can do what we did back in 9.7 example 6. So we looked at an example where I think we did like natural log of 2 or something like that. And we said, what value of n do we need? Like how far out do we need to take the polynomial in order to get a decimal that's accurate to within 5 decimal places or whatever. So we did an example like that. Now, I'll be honest, your textbook here gives you some more examples, and most of the homework problems are examples of doing exactly this kind of thing that we did back in 9.7. I'm not exactly sure why. It's like, so I like your textbook generally. I do like this textbook, but I think this particular section, they emphasize the wrong thing because they really go overboard. Like like on a whole bunch of homework problems doing stuff like this, like calculate sine of 3 degrees to within 10 decimal places of accuracy, and it's like, those kinds of problems to me are very tedious. And anyway, it's the wrong thing to be emphasizing. What we really need to be emphasizing is this fact right here, right? That we shouldn't take for granted, right? But the fact is that the series will converge to the function if the remainder disappears, basically, as n gets really large, right? So that's really the main takeaway. And so consequently, like, you're not going to have a lot of homework on this section. This is mostly just like a theory thing. Like, I think this section is important because of the theoretical aspects behind it, but I'm not going to, like, on a test or quiz, I'm not going to be like, calculate natural log of 12 to within 14 decimal place accuracy or something. I mean, that's just kind of like, I'm not interested in testing on that kind of thing. And you've seen some examples of it back in 9.7 already, so I just don't see the need to rehash all of that. And then another thing that your textbook does in this section is it shows on certain series how some series can be manipulated to give us other series that are sometimes a little bit more useful. But the thing is, that's going to be the main topic of discussion in the next section. So again, I don't really see the need to talk about that here. So really the main takeaway is this thing, right? That you can show, not always, right? But in some cases, you can show that the series will actually converge to the function that it's supposed to be approximating or representing. And so that's a really big, important result, and that's kind of the main takeaway. I did want to talk about that binomial series, though. So just the last thing real quick that I want to talk about was this last one here, this binomial series. So 1 plus x to the m equals 1 plus this kind of weird, crazy looking thing. So a couple things to say about this. So that series is called the binomial series, and it says this, right? So if m is any real number, well, I'll talk about this in a second. So if m is a real number but not, say, a positive integer, okay, then for any value of x, or the absolute value of x is less than 1, you get this. So this is the interval of convergence here for this particular series. And what's cool about this is that m can be any real number. So it could be like 1/2, right? So in other words, you could approximate the square root of 1 plus x by this polynomial where m is 1/2, right? So it's a really cool result. In the case where m does equal 0, 1, 2, or whatever, then 1 plus x to the m would just be a polynomial, right? It would just be like 1 plus x to the 4th power. And you may be familiar with the binomial expansion for these kinds of things, back from your algebra days. Maybe you didn't ever cover it in algebra, but either way, right? You may be familiar with this kind of thing, which says that, hey, 1 plus x to the m, assuming that m is a positive whole number, is just this sum from k equals 0 to m of m choose k times x to the k, right? And this thing, unlike this one, the radius of convergence, or the interval of convergence on this one is -infinity to +infinity, right? Whereas here it's just -1 to +1. So, you get a little bit stronger statement if m is a positive whole number. And you may think, but that doesn't look like that. They are pretty much the same, right? Because m choose k, the binomial coefficients m choose k, are defined as m factorial over k factorial times m minus k factorial. And if you work this out, right, you can cancel off a bunch of stuff up here. If you write m factorial as m times m minus 1 times m minus 2 times m minus 3, all the way down to m minus k factorial, then the m minus k factorials will cancel, and you'll be left with m times m minus 1 times m minus 2, all the way to m minus k plus 1 in the numerator. And you'll be left with the k factorial in the denominator. And that's just exactly what you have up here. But the other difficulty with writing this down writing down the theorem in this way is that it's a little confusing, because if m is not a positive whole number, like if m is -5, then what does -5 factorial even mean, right? We haven't defined the factorial for negative numbers, or for that matter, what would if m could be any real number, so m could be like pi. What is pi factorial, right? So it's not clear when you write down the theorem in this way. It's really assumed that m is a whole number. So if m is not a whole number, then you kind of have to write it down this way. But it's cool that that the equality still does hold. Notice also that here the index starts at 1 and here it starts at 0. That's because when k equals 0, that's where you get this first term, the 1. That's where you get that from, right? Here it's kind of wrapped up in the same thing, because if k is 0, then m to 0 is going to be 1 for any m, and x to the 0 is going to be 1. 1 times 1 is 1, and so that's where you recover that kind of first term. Anyway, all of that kind of complicated mess to say that we've got a really cool result, right? Another big thing to point out is, of course, here we have an infinite series, and here we have a finite sum, right? That is, so if m is just a positive whole number, then you don't have to go all the way out to infinity. Although this formula would still work, because for any value of m, like let's say when k equals, like let's say that m is 3 and k is 4, right? Then m minus k plus 1 would be 3 minus 4 plus 1, which is 0. And so then that just goes away. And then if k is 5, then from that point on, from k equals 4 onwards, you're always going to have a 0 in the numerator, and everything's going to cancel off anyway. And so this is just going to end up being a finite sum if m is a positive whole number. But if m is not a positive whole number, then you never get a finite sum up here. And so anyway, or rather, you never get zeros up here, is what I should say. But anyway, I think I've done enough talking. Let's do a couple examples. Oh, well, one more thing to say. Sorry. And then we'll look at some examples. As far as the proof goes, I'm not going to prove this thing in detail, but I did just want to give you a little sketch, right? So if we have this function here, and we're trying to write a Taylor polynomial for it, or better yet, a Maclaurin polynomial for it, the first thing we have to do is come up with a formula for the kth derivative of this function evaluated at x equals 0. So to that end, right, note that if f of x is 1 plus x to the m, then f prime is m times m 1 plus x to the m minus 1. F double prime is m times m minus 1 times x plus 1 to the m minus 2. F triple prime would be m times m minus 1 times m minus 2 times x plus 1 to the m minus 3, and so forth. And then if you evaluate those things at 0, f of 0 is 1. F prime of 0 would be m times 1, which is m. F double prime of 0 would be m times m minus 1 times 1 to the m minus 2, so just m times m minus 1, and so forth. So the kth derivative evaluated at 0 would be m times m minus 1 times m minus 2, and so forth, all the way down to m minus k plus 1, right? Which is exactly what you get here. So this is the kth derivative evaluated at 0 divided by k factorial times x to the k, right? And there it is. It can also be shown using the ratio test that this thing converges if the absolute value of x is less than 1. And then the last thing we'd have to do is show that the limit as the remainder, the limit as n approaches infinity of the remainder is equal to 0, which I'm also not going to do. But that's sort of a sketch of how the proof would go. Okay, so now let's look at some examples. So let's find a binomial series for each of these guys right here. So I want to find a binomial series for 1 over 1 plus x squared. And the reason I want to give you an example is because this formula can be a little bit confusing to use. But okay, so notice that first of all, this is 1 plus x to the negative 2, right? So m equals negative 2, okay? So 1 plus x to the negative 2 is going to be 1 plus the sum from k equals 1 to infinity of negative 2 times negative 2 minus 1, and so forth, all the way down to negative 2 minus k plus 1 over k factorial x to the k. So if you think about what the first few terms of this would look like, okay, when k equals 1, in the numerator, we're going to stop at k equals 1. Negative 2 minus 1 plus 1 is just negative 2. So we're just going to have negative 2. It's going to be negative 2 over 1 factorial times x to the first. If you plug in k equals 2, then here in the numerator you're going to have negative 2, and then you're going to stop at negative 2 minus 2, which is negative 4, plus 1, which is negative 3. So you're going to stop at negative 3. So you're going to have negative 2 times negative 3, and that's as far as that's going to go, over 2 factorial x squared. Okay, and then if k equals 3, you're going to have negative 2 times negative 3 times negative 2 minus 3 is negative 5, plus 1 is negative 4. So you can have negative 2 times negative 3 times negative 4. So I think you kind of see where that's going, right? Over 3 factorial x cubed. So my goal is to kind of try to rewrite this in a closed form so that I have like a closed formula for this. So first of all, let's fix up the negatives, right? It looks like I'm going to have an alternating thing, right? So this is going to go on and on. I can write out the next one pretty easily because I see the pattern now. Negative 4, negative 5 over 4 factorial times x to the 4th, right? And it's going to go on and on and on. But I think I'm going to pull out the negatives. And maybe I'll call this thing 0 factorial, right? So maybe I'll call it like 1 over 0 factorial. And this thing I'll call minus 2 over 1 factorial. Ooh, and I can call this x to the 0, right? X to the first. And then I can do plus 2 times 3. Oh, maybe I'll do this. Okay. Over 2 factorial x squared minus 1 times 2 times 3 times 4 over 3 factorial x cubed. And then plus 1 times 2 times 3 times 4 times 5 over 4 factorial x to the 4th, and so forth. So it looks like I've just got a factorial up here, right? And in fact, I get a lot of cancellations because 4 factorial is 4 times 3 times 2 times 1, so that cancels all of that, and I'm just left with a 5. 3 factorial will cancel that stuff. 2 factorial will cancel that stuff. Okay, so I'm really left with this. X naught minus 2x to the first plus 3x squared minus 4x cubed plus 5x to the 4th. And then I guess the next one would be a minus, right? So rewriting that as a sum now. By the way, this is a 1. So I think I can write this as the sum. If I call this x to the k, then this is k plus 1, right? So I'm going to have k plus 1 x to the k, and I'm going to go from k equals 0 to infinity. And then as far as the signs are concerned, I'm going to have a negative 1 to the k, I think, because I start positive, right? And then negative, positive, negative. Right? And so there you go, right? So 1 over 1 plus x squared equals this thing, provided that absolute value of x is less than 1. So there's the answer to the question. So that's kind of cool. Let me give you another one. So let's do this for 1 over square root 1 plus x. Okay, this thing would be 1 plus x to the negative 1/2. So m is negative 1/2 here, right? Okay, so 1 plus x to the negative 1/2 equals 1 plus the sum from k equals 1 to infinity of m times m minus 1, right, times m minus 2, and so forth, all the way to m minus k plus 1, divided by k factorial times x to the k. Okay. So that's 1 plus. And then let's think again. So if k equals 1, then I'm going to stop at negative 1/2 minus 1 plus 1. That's just negative 1/2. So I'm just going to have a negative 1/2 over 1 factorial. If k equals 2, then I'm going to stop at negative 1/2 minus 2 plus 1. That's negative 1/2 minus 1. So I'm just going to stop at the first two terms, right? So it's going to be a negative 1/2 times negative 1/2 minus 1, which is negative 3/2 over 2 factorial. Oh, and I forgot the x to the first. If k equals 3, then I'm going to stop at negative 1/2 minus 2, right? I'm going to have negative 1/2 times negative 3/2. Negative 1/2 minus 2 would be negative 5/2. I'm going to do one more term. So if I stop at k equals 4, that means I need to stop at negative 4 plus 1 is negative 3. So I need to stop at negative 1/2 minus 3. So I'm going to have negative 1/2 times negative 1/2 minus 1 times negative 1/2 minus 2 times negative 1/2 minus 3. Okay, over 4 factorial times x to the 4th. And then this is going to keep going. Okay. So let's see if I can come up with a closed formula for that monstrosity. Holy schmoly. Okay. So, goodness gracious, this one is a little bit more complicated, isn't it? So I've got 3 factorial, and here I'm not doing 5, 4, 3, I'm just doing 5, 3, 1, so I'm only doing the odd numbers. That's interesting. I don't know if I'm going to get anything really all that nice out of this as far as cancellations and stuff go. I think I'm going to have 1 minus 1/2 x to the first. Okay, here's what I can do. I can call this 1 minus 1 over 2 to the first times 1 factorial x to the first plus 1 times 3 over 2 squared times 2 factorial x squared minus 1 times 3 times 5 over 2 cubed times 3 factorial x cubed plus 1 times 3 times 5 times 7 over 2 to the 4th times 4 factorial x to the 4th, and so forth. Okay. So can I write that as a sum now? Sure. In fact, I wonder if I can continue the process here. Like I could call this 1 over, it would have to be 1 to the 0 times 0. Sure, yeah. So I can call this 1 over 1 to the 0 times 0 factorial times x to the 0. So I think what I end up with is this thing. I've got sum from k equals 0 to infinity of, well, the numerator's a little tricky, isn't it? 1 times 3, 1 times 3 times 5. This is when k equals 0, k equals 1, k equals 2, k equals 3, k equals 4. So I think the stopping point is at 2 times k minus 1, right? Because here k equals 3, 2 times k is 6, 6 minus 1 is 5. Here k equals 4, 2 times 4 is 8, 8 minus 1 is 7. So I think you stop at 2 times k minus 1. So it's like, oh, and that's where it breaks down here on this first one, right? Because if I do this for k equals 0, then I would get a negative 1, wouldn't I? So, okay. So I think this is just going to have to be 1 plus the sum from k equals 1 to infinity. And then first of all, the signs alternate, so I'm going to have a negative 1 to the k. Second of all, I think I'm going to have 1 times 3 times 5 and so forth, all the way until I get to 2k minus 1. And then I'm going to be dividing by 2 to the k times k factorial x to the k. That's not very nice at all, but that's the binomial. That's the binomial series for that, for 1 over square root of x. It's 1 over square root of 1 plus x. And I guess it should go without saying, I mean, what's nice about all these, of course, if you wanted to know what 1 over, square root of 4 is, well, no, that wouldn't work, because x has to be between negative 1 and 1. I guess if you want, well, so it would have to be a very specific thing. Like if x is 1/2, then you get square root of 3/2. So you get 1 over square root of 3/2, or in other words, square root of 2/3. Right? So if you wanted to approximate square root of 2/3 and you didn't have a calculator handy, well, you could do this, right? Goodness, who would want to do that? But anyway, that's that. So that's all I have to say.